Hello everyone. In our previous video, we have discussed the definition of topology. A topology on a non-empty set capital X is nothing but the collection tau, which are the subsets of X, should satisfy some properties. We call three properties. First one is X and empty should belongs to tau. Second one is the union of members of tau be again the member of tau, and the third property, the intersection of members of tau is again the member of tau. As we know, if tau is a topology on X, then by our definition X and empty are tau open sets. The union of any number of open sets is again open set, and the intersection of finite number of open sets is again open set. This is one of our major basic properties of a topology. A topological space is not just a set capital X. It is a pair X comma tau. That's why we have X comma tau is an ordered pair, which is a topological space. And here tau is a topology derived by capital X, or topology defined on capital X. Let us consider one example. Let capital X be a non-empty set and tau be the family of all those subsets capital A of X such that either capital X minus A is finite or capital X minus A equal to X. Let us find the meaning of this statement. Here tau be the family of all subsets A of X. So we need to define tau, which is the set in which we have A is the subset of X, such that either here X minus A is finite or X minus A equal to X itself, right? X minus A equal to X itself, which implies here A be the subset of X. Either X minus A can be written as A dash, that is complement of A, which is finite, or we need X minus A equal to X itself. Here whenever we are subtracting any set from X, we should get X itself. It will be obtained whenever the value of A is empty. If we subtract any finite quantity from X, then will not get a complete X itself, right? So if it is empty, then only we get X minus A equal to X. So again we can write this as A is the subset of X such that A dash is finite. We can write or as union, right? Union empty. Okay, this is the meaning. Now we call this tau as topology. This tau became topology on capital X. We call this topology as finite complement topology. Finite, here A complement is finite, so finite complement topology. Sometimes we call this topology as Zariski's topology. We derive this topology on capital X, so Zariski's topology on capital X. Okay, let us derive this. Let's go for the solution. Let's check how this set become the topology. By hypothesis, we have empty belongs to tau, right? Empty belongs to tau. So the first condition for the topology, empty belongs to tau. Also we have a dash is finite. Let us consider the value of a as x. It will become x dash. We know that x dash is nothing but empty, right? X dash is finite. X dash is finite, which implies here if a dash is finite, then a will be the element of tau. That implies x also the element of tau. Therefore, from these two we can write x and empty belongs to tau, which is the first condition, first property of topology. We have proved this. Let us go with the next property, which is for union. What is the property here? We know that the union of members of any subcollection of tau is in tau. We prove this by using this result. If the set G lambda, provided this lambda belongs to index set, is a collection of members of tau, then union of this G lambda, collection of members, should belongs to tau. This is the second property of topology. Right, let's prove this. Let us consider the set G lambda, provided this lambda belongs to index set, be a collection of members of tau. Then G lambda belongs to tau for each lambda belongs to index set. Therefore, by definition, we know that G lambda belongs to tau. Here they had given tau is nothing but A be the subset of X, right? A be the element of tau. We consider G lambda be the element of tau, which implies if A is the element of a tau, then either A dash is finite or A equal to empty, right? So here G lambda be the element of tau, we write G lambda dash is finite. We can write for each lambda belongs to index set. Since, as we know, since arbitrary intersection of finite set is also finite, we can write intersection of G lambda dash is finite. Intersection of G lambda dash can be written as union of G lambda the whole dash. This is by De Morgan's law, right? Union of G lambda dash is finite, provided this lambda belongs to index set as usual. So we can write here intersection of G lambda dash, provided lambda belongs to index set, is nothing but union of G lambda the whole complement, provided lambda belongs to index set itself. Here union of G lambda dash is finite. We got union of, instead of A we have union of G lambda dash. Union of G lambda dash is finite. Union of G lambda dash is finite implies, by the definition of a topology defined here, union of G lambda, where lambda belongs to index set, belongs to tau. So this was the second property we need to prove given tau became topology. Let's go for the third condition, which is for the property of intersection. Property says that the intersection of members of any finite subcollection of tau is in tau. Here finite subcollection. So let's consider two sets A and B, which are the elements of tau or member of tau. If A and B are elements of tau or member of tau, which implies by the definition of tau given in the example, A dash and B dash should be finite, right? Are finite. We know that union of two finite sets is again finite set. Here A dash and B dash, we know that these two are finite. Union of finite sets, union of two finite sets is again finite. So A dash union B dash is finite. We can write A dash union B dash as A intersection B the dash complement. A intersection B complement became finite because by De Morgan's theorem we know that A intersection B complement is nothing but A complement union B complement. So we got to know A intersection B whole dash is finite. Again, by the definition of tau defined here, we can tell that A intersection B belongs to tau, because the definition they have told either A dash is finite or A equal to empty. Here we got the condition A dash is finite. A instead of A we have A intersection B, right? A intersection B complement is finite implies A belongs to tau. So here A intersection B complement is finite implies A intersection B belongs to tau. This proves that intersection of any two members of tau is a member of tau. Therefore, finite intersection of members of tau is a member of tau, since here A and B are arbitrary sets, right? That's why. Therefore, by the above three results, we can tell that the tau defined above is topology on capital X. Okay, this topology is called finite complement topology on X or Zariski's topology on X. Let's learn some more in our next video.